In this video, we're going to talk about how to solve systems of linear equations when there are two variables involved. In the next section, we'll do the same, except we're going to look at equations where there are three variables involved. First, let's talk about this conceptually. If there are two lines, there are three possible scenarios for how those two lines are going to interact. First, it could be that the graph of the two lines intersect at one point. In that case, we say that there is one solution to the system of equations, and the solution is the ordered pair that represents that point of intersection. In that case, we say that the system is consistent, which means that a solution exists. Also, because the two lines are distinct, they are different lines, we say that the system is independent. Another possible scenario is that the two lines, when graphed, don't intersect. This happens when the two lines are parallel. Because there is no point of intersection, there is no point that satisfies the conditions of the two equations at the same time. In this case, we say that the system has no solution. Because the system has no solution, we say that the system is inconsistent. However, because the two lines are distinct, they are different lines, we say that the system is still independent. Finally, a third scenario is that when we graph the two equations, they end up being exactly the same collection of points. They end up representing the exact same line. So you can think of it as one line tracing above the other. In this case, every point on the line is a point of intersection. Because points of intersection represent solutions to the system, there are solutions. In fact, there are infinitely many solutions. Every point on the line is a point of intersection and therefore a solution. In this case, we say that the system is consistent because a solution exists. There's just infinitely many of them. But because the two equations represent the same line, not distinct lines, we say that the system is dependent. All right, let's take a look at two methods for solving systems of linear equations now that we have this background of the conceptual understanding of what is happening with these graphs. We're going to review two methods for solving linear systems. First, we'll do some examples where we solve using a method called substitution. In the substitution method, we choose one of the two equations and we choose one of the two variables to isolate for. And then we substitute that representation into the unused equation. Then we'll have to do some back substitution to solve for the other variable. We're going to practice this method first, and then we'll come back and do some additional examples using the elimination method, also known as the addition method. First, let's practice with substitution. In the first example, we have a system with the following two linear equations: x plus y equals 5 and x minus y equals 3. Here, we can choose either of the two equations and choose either of the two variables to isolate. So just for simplicity, I'm going to isolate the x variable in the first equation. So I'm going to subtract y from both sides. Now, in the unused equation, which in this case is the second equation, instead of y, I'm going to write what y is equal to, which is negative y plus 5. So I'm going to write negative y plus 5 instead of x minus y equals 3. So right here, where we substituted the negative y plus 5 for the x, is where the substitution took place. Notice that now we have a single equation with one variable, in this case, just the y variable. Let's go ahead and solve for y. Combining like terms, we have that negative 2y plus 5 equals 3. If we subtract 5 from both sides, we get negative 2y is equal 3 minus 5 is negative 2. And dividing both sides by negative 2, we have that y is equal to positive 1. So we have solved for y. Now we still have to solve for x. Now, remember that equation that we manipulated right at the top? It's solved in terms of x. So all we have to do now is back substitute what y stands for. In this case, we found that y is equal to 1. So x is equal to the opposite of 1 plus 5. In this case, we have that x is equal to 4. That means that this system has one solution, and it is the ordered pair x equals 4 and y equals 1. And because this is an ordered pair, we're going to put this in curly brackets to indicate the set containing this one ordered pair. In this case, we have a system that is consistent and independent. So there is one point of intersection. That point is the solution to the system. And we have two distinct lines. Let's do something similar with the next example. In this case, we have 2x plus 4y equals 8 and 4x plus 8y equals negative 16. This one makes it a little bit less straightforward which equation to use first and which variable to solve for. It really doesn't matter. It's a matter of preference. So I'm going to take the first equation and let's isolate y in this case just to be different. So first I'm going to subtract 2x from both sides. And I'm going to divide both sides by 4. So I get y is equal to negative 1/2 times x plus 2. Now, in the second equation, I need to substitute this value of y where I see the variable y. So in this case, I'm going to use 4x plus 8 times what y stands for equals negative 16. Well, what y stands for is negative 1/2 times x plus 2. Now, let's work through cleaning this up a bit. So we have 4x. 8 times negative 1/2 is negative 4, so we'll have a negative 4x. And then 8 times 2 is 16. And then on the right-hand side, we have a negative 16. Now look at what happens when we try to combine like terms. 4x minus 4x is 0. So we're left with 16 is equal to negative 16. Well, this is a false statement. It's never true, regardless of what value of x we choose. This is what we call a contradiction, a statement that can never be true, regardless of our choice for the variable. That means that there is no solution to this system.